in chapter number 5. Let's go to the here. Two-board approach. We finished this cascade. We studied this. Darlington hybrid model. Today we'll continue to talk about hybrid equivalent model. Before we talk about RE model, and today we'll talk about hybrid model. Today we'll talk about what is hybrid model. Okay. RE model, as you see with me in the video, is, let's close this, has advantage that the parameters are defined by actual operating conditions. The parameters of hybrid equivalent circuit or model are defined in general. Let's explain more. It's returning back to the, when this, yeah. For example, if I return back okay. For example, for RE model, we have RE for common emitter and RE for common base. مثلا here beta RE beta IB. Here I have RE, I have up alpha I. So see here we have different arrow, one down, one up. One is down here like this one is up like this for common base. Now in hybrid model, so RE is correct, very correct one. But can we make a model that can mix both? I need to mix the hybrid model. So RE model is a very good model, but in RE we have RE for common base, RE for common emitter, and both are different. So in hybrid model, we want to create a model that can mix both in one model. So this is the benefit of hybrid model. Let's see hybrid model here. Hybrid model is defined in general term for any operating conditions. Here for actual operating condition, here for any frequency. Let's see the hybrid model. In hybrid model, we have those parameters, something called HIE, HRE, HFE, HOE. I will explain, wait. And this is for any model, minimum, maximum. And this is the condition IC, for example, 1 milliampere. DC is VC is 10 volt DC, frequency is 1 kilohertz, so we can find these parameters. Let's directly go to the explanation. For any circuit, we can say the circuit has two ports. I have two ports. This is port 1. This is port 2. And usually see with me here, I is inner, IO is inner also. VI, VO, ZO. This is our system. This is our system. I want to find the system based on hybrid model. How we can do this? Okay, let's start directly with this. If I return back to the C, you have this formulas. First one, VI is H1II. This is by the way, this is okay. I'll explain something. For two port models, we have four models, not one. First one is Z model. We have Y model. We have hybrid model. Last one, we have S model. So I guess in circuit 2 you study these models. Z model, that means it's V as a function for I. Y is model, this is for Z model. Y is model is I as a function for V. Hybrid, that means V as a function for I and I as a function is equal for V. Is this another thing? It's called Z model, Y model, hybrid model, and this is for S model. We are using S model for power usually, for high voltage. In our study, we'll focus about this one, hybrid model. So for two port model, we have four models. Z models, it's V as a function of I, Y is as a function for V. In hybrid, we have both. Now we can see. And this is for power for high frequency. Now, let's see the formulas for hybrid model. Let's take this. Copy. Up. And we go here. Yes, here. Now, let's see this hybrid model. As I told you, hybrid is V as a function of I and I as a function of V. See, so for that reason that you have called hybrid. Hybrid, we have both. Okay, so let's see here. It is VI. It is here. This is called here H11 AI and H12 for VO or for V2. I can write like this one. V1 equal H11 self parameter with I1 plus C. H and relationship between 1 and 2 with V2. The effect from 1 to 2 in V2. Now, I1 is, see, this is as I told you before, this is V as a function for I, this I as a function for V. So this is called hybrid. Okay. Continue. It is I2. It is H21 for I1. Same parameter here, plus H22 V2. Here we have two. Let's study this. Here we have this parameter. See this parameter. H11, H22. H11, we can see this is self parameter for input. H22 is self parameter for output. And here I have 1, here I have 2. So V1 and I2. V1 for H1, I2 for V2. Okay. Let's continue with this. Here I have H2, H11, here I have H22, and here the effect from output to input, here the effect from input to output. So in hybrid model, we have 4 parameters. H11, that's mean the effect from input or self effect for input to input. H11, the effect from input to output. How can input affect to output? And H21, the effect from output to input. H22, the effect from output to output. Okay? Now, let's see what are these parameters. Let's go here. I want to find these parameters in this one. So first of all, if I want to find, for example, H1, I will cancel this. So H11 equal VI over II when the VO is 0. VO 0, that's mean, when it VO 0, 0, 0, volt 0, volt 0, that's mean, open circuit. Open or short, what do you think? Yeah. Open or short? Short circuit, thank you, Ahmed. So VO 0 will be short circuit. I will go here to output and close. This is H11. And again, same thing for H21. I will make short circuit so I can find H21. It is IO over I for short circuit. Or when the VO is 0. Now another thing, I want to find H12. So H12, I will cancel this. It is VI over VO, this is H12. So VI over OVO. I0, this is 0. So it is I1 is 0. Current 0, that's mean open circuit, no current. So here we have two cases. One time will open circuit, another time will be short circuit. Then to find the relationship between input with input, input with output, output with input, and output with output. Let's see here in our book this explanation in details. See here, H11, when the VO is 0, short circuit, the output terminal. So we can find H11 as explained to you. Now, another one, H12, see here, H12 this, it's open circuit. By opening the input leads, the following result is this one. And H12 is volt over volt. So we can say it is unitless, without any unit. Volt over volt. And this is called open circuit reverse transfer voltage ratio parameter. The effect from input volt to output. But here you have the word reverse. In H12, we will study the effect from H21. So H12, that means how 2 would affect to 1. And if I have VO, is this VO will affect to VI? This VO can change VI or no? This is VR. For that reason, we can say this is reverse transfer voltage. How the output will affect to the input in voltage. Now, third parameter is this one. Reverse here includes because the ratio is input voltage over an output rather than the reverse ratio typically is inverse. Okay, interesting. Usually this reverse voltage or H12 usually it's very small, so we can ignore it. But before this reverse voltage has a meaning called early effect. Early effect. I will write here. You can say about early effect in transistor. This effect called early. This is a science effect. And this early effect explained the output effect to the input effect in voltage. Now, third parameter is H1, H21, 21. Here H21 it is, see here, it's current over current, IO, II. How can II affect to the IO? IO based to II. Or here, if I explain H21, how can 1 affect to 2? You can express as you want. So how is the first input affect to the output? And here is current over current. Current over current. That means unitless, without unit. And this is called, if you want the name here, circuit forward transfer current ratio. Current, that means from input, for that means from input to output. And this is, as you see, subscribed to 1. Again, indicate that it's transfer parameter with output in the numerator and the input in denominator. Last parameter is H22. It's I over VO. When I is 0. So because it's a ratio of output to input, so this is in Siemens or O minus 1, and it's called open circuit output admittance parameter. If I open I current, if I open the input, I can find this for output. So how we can find these parameters? Actually, you have 2 ways. Short circuit for output, open circuit for input. Then you can find these 4 parameters. These parameters start with this one. I will show you here the last parameters, this one. Complete hybrid model. This is the complete hybrid model. And this is very important for exam. I have here HI, Z. This is dependent voltage source. This is dependent current source. And this admittance that we talk about. This is in Y, in Siemens. This is unitless. And see the direction of arrow from up to that. So this is the complete hybrid equivalent model, and you can compare with, and based on this, we can compare this model with RE model that we studied before. So H11, as you see here with me, is input resistance. H12, 1, 2. See here, we can say H1, 2, but meaning that means effective from 2 to 1. H1, 2, that's mean effective from 2 to 1. You can find in this one, in this HR reverse. Now, opposite case, H1, 2. It's H1, 2. Now H2, 1. H1, H2, 1. So H1, 2, H2, 1. And this is H2, 2, H1, 1. Here we can know, okay, the big confused us how we can H1, 2. It should be from 1 to 2. No, here effect from 2 to 1. Effect from 2 to 1. H2, 1, that's effect from 1 to 2. So usually for our study, okay, Hujam, we have this and it's enough. We have this input and output. Here we study two also extra parameter. Effect from out to input, this one, and effect from input to out in this one. And as you see here, we have dependent volt source, dependent current source. Any question until now? It's clear? How we can use this one for transistor now? How we can apply this for a transistor? Okay, I will show you for common emitter and for common base. Just wait for 1 minute. I will return back to you. Just wait for 1 minute. Excuse me. Now, let's compare and apply this model here for common emitter and for common base. This for common emitter, I have IB as in, IC as out. So this IB as in, IC as out. And it's common. So each right parameters, H11, H2, H21, H12, H22. H11, that's mean HI, and here we'll add something, etc. E. E mean here common emitter. Got? So here we have HIE. Clear, Ahmed? Wait, it's HIE. H-I-E. Okay, now we have here H-R-E, H-O-E. This is H-R-E, H-F-E, H-O-E. E. E here indicates the common emitter. HFEIBHREVCE, air input and output. And same thing we will find for common in base. Because it's common base, explain this here. I have also HIB, HRB, HOP, HFP. And see the same model in common base and common emitter. We have the same thing for common base and common emitter, no change. We have the same thing, just we change this context from B to BI or I to BB. And this is the benefit for hybrid. We don't have any change. If you remember, as I told you before, for example, for RE model, we have model for common emitter and we have model for common base. We have one for this, one for this. Here we have one model, uniform model for common emitter and common base at the same time. So for that reason, we can say it is hybrid. We prefer hybrid. If you open any data sheet for transistor, you can find this data sheet has written by hybrid model, not RE model, because they are using the COM model. See this before? We have like this data sheet here in our book. No, we don't have any quiz today. Hamza. No. Who said that? Who said that? We don't have any quiz today. We finished. If there is a quiz, I will announce Hamza. See this one here. No, it's wrong, Hamza. Okay. After the lecture, we can talk. But we don't have. See, here we have this, for example, input impedance for HIE. Here, voltage feedback ratio, HRE, small signal current gain, HFE, output admittance, it is HOE. So you can see from this one with me, that's we have same thing for common base and common emitter. Now, how we can apply this in our study? Now, how we can apply this? Actually, if you want to save your time, which one will HRE? HRE usually is very small. The effect is very small. So I will read here. Where is it? HFE and HOR, it's not included is this model because for common emitter and common base configuration, the magnitude of H F and HO is often such that the result obtained from the input impedance ZI, ZO, and V and AI and are both largely affected if HR and are not included in this model. Usually, if R or HR is normally relative small quantity, HR, it's removed, it's approximated by HR equals 0, and resulting the short circuit for this one. So usually, I will short this one. Usually, HR is the effect from output to the input, and this is very small, so we can ignore this one. And HO is the effect from output to output, also very small, so we can ignore these two parameters. So I can write HRE and HOE, HRP, HOB are very small, so we can ignore. So now we have HI for both and HF for both. So this is the approximated or approximate hybrid model. Short one. This is a full view. This model is the full view. What is this? This one. Yes. This is the full model. If I ask you what is the full model, this is the full model or complete model. But usually we will cancel this short circuit and open this. So just we will focus on this and this. Input and transfer from input to output, how input can affect the output, or each forward, each forward, each forward, the effect from input to output. Effect from output to input is very small, so we can ignore. And the output with output also we can ignore because it's very big. For example, if you remember RO in RE mode, it was output in kilo ohm. So you can say it's open circuit. So also we can ignore. One is short, one is open. So for both, we can ignore this one, and we got to use this one in our study. See this, the model that we're going to use here, this model. This is the model that we're going to use in our study. So we have two models, full model, and this is the approximate hybrid model that we are using in our study. Now, how we can find this HI, HF? Easy way. We'll start from RE model, then we will apply for hybrid model. It is start from RE, go to hybrid. How we do this? This is advice for you. See here in our book what he said. Go up. The hybrid equivalent RE model for each configuration are repeated. So if I draw again with this one and this one, this is the equivalent between both. Excuse, stay with me, it's very important. Here, for example, it's RE, here it's hybrid, H. This is common emitter, this is common base. So let's compare. Ahmed, with me. Beta RE equal HI E. Beta IB equal HFE. Okay, let's make again hybrid RE, common emitter, common base. Now focus on the number HIE, it is beta RE. IB with IB, so HFE, see this, HFE is beta. Same thing here. HIP, it is RE. IE, HFP, IB, IE. Here we have wrong. HFBI No, it should be HIE. Just a minute, just a minute, just a minute. We have mistake. Yeah, HIE. Here HIE, sir. In your book is wrong. HPIIE. Equal alpha IE. So this is IE. Correct this. In your book we have mistake wrong. This is because here HFB with input. Input here is IE. So this is IE. Correct in your book. It's wrong. If you have a book, correct this one. Excuse me. Here is input. So this input. Which page? Which page? Which page? Just a minute, Ahmed. This is wrong in your book. It is 323, 323. 323. See this? It's comparison. Here. Okay, now it's correct. So excuse me, correct at your book. Here we have IE and this is IE. Like this. Alpha IE. Did you correct? All. Okay, so let's continue with this. Now, comparison can find here. HIE. HIE is beta. RE. HFE is beta. AC. Just beta AC. Now for common emitter, HI. For common base, HIB. This is HIB. It is RE and HFE. Take care. Here. Here, you are. See, here we are. See, let's talk about this one. HFB, arrow down. Here, arrow is up. So HFB equal minus alpha. Clear why it's minus? Because in hybrid, it's common model for both common emitter and common base. So for common base, common emitter, same. For common base, we are gonna use minus because of its direction. Clear for you? Got it? Yeah. So take care about minus. Now let's start to solve example. Given IE 2.5 milliampere, HF, FE, HOE, HOP, and determine the common emitter, the common base RE model. So again, I want to start. I ask myself, HIE, it's beta RE. For that reason, we're gonna, if in hybrid model, we're gonna use, so when it start from RE, then come to hybrid. For that reason, we studied hybrid, the RE, then hybrid. You have to start with RE. IE is exact correct model, but it's approximate model, and it's practical model, RE model. So here, if I want to solve this question in hybrid model, RE here is 26 millivolt over RE. I start to calculate RE in this way. Then HIE, as you see here, it's beta RE. RO, it's 1 over HOE. HOE is in Siemens. RON. He gives you HOE. So he asked me the common emitter hybrid equivalent circuit, the common base RE model. In this question, he asked two things. I asked me common emitter hybrid, common emitter RE model. So for common emitter, this is we have here HIE, and here we have HFE. And he also he gives to me HOE. So I will calculate this here. HFE given, HFE is this given, and HOE also is given. Now, another one, the common base here, common emitter, RE model. He wants RE model, so here we have RE up, alpha IE, then we have RO. R, he also gives me HOP, so RO 1 over HOP. So let's see the models here. This is the first model. And it's another model for common base. RE 10.4 ohm, IE up, alpha usually 1. RO is 2, RO is 1 over HOP, it's 2 mega ohm. So this is, as you see here, how we can move from hybrid model to RE model and from RE model to hybrid model. Any question about this? Now, how we can apply those, see this? Approximate common emitter hybrid model equivalent HIE, HFP, and 1 over HOE, 1 over HOB. This is the if I want to add HOE and HOB as ohm, not Siemens. So we can if you write here Siemens, keep at it. If you want to convert as ohm, you have to divide by 1 or flip it. You have to flip it to be as ohm. Now, fixed base configuration with hybrid model. Same thing. Exactly same what we said before. Exactly. If you understand. So start from RE, go to hybrid. So this is the model that we said before, HIE, HFE, and 1 over HO. Then you can add the rest even HBRB and RC. Now, I want to find parameter AV, AI, ZI, ZO. So this is ZI, ZO, easy, directly from the model. So see this, ZI is RB with HIE. It was there beta RE.
ماما حطيتهم الجوال بعدين حط أول شي حط لبس بعدين سي باليرينا.
Then here, 1 HOE with RC. Now, AV, it's VO over VI. It's minus. Okay, what is this? It's hard. Not hard. Let's start to analyze this. AV before it was, yes, minus RE down RC with RO. Okay. RE here is, we don't have RE, we have HIE, it is HIE. Oh no, we don't HIE. Okay, beta RE. Beta is HIF. HIF. So just a minute, it's wrong. HFE, correct. Beta is HFE. So RE is HIE over HIFE. Good. Change here minus RC. RO is 1 over HOE. Here it is down. Take this one. HIE, flip it. HFE. Here it's wrong. HFE, correct in your book. Also, this is wrong. It is HFE, not HII. Here, HFE, not HII. We don't have double I. This is how we can find this one. So this is HFE, correct, Ahmed? Sirs, correct here. It's HFE. If you don't want memorization, use my method. Start with RE, then go here. Is it clear? Did you change in your book? Aryan, Ahmed, who is also with me. Change this. Jamal, Ahmed Jamal, I guess. Najm. This is wrong. AI, it is IO over I, it's HFE. Now, for this network, question ZI, ZO, AV, AVI, determine this direct implementation for formulas. Now, voltage divider, same thing that we explained. We have ZI, ZO, AV, and AI. See here in this one, corrected. They are corrected, this one. See, HFE. Same formula for both. Here also, it should be HFE. This is F, not I. Voltage divider, same thing. You have to calculate Thevenin to calculate RE, IB, start with DC, calculate IB, IE, RE, then continue with these parameters. Clear? Is it hard or easy until now? Now, unbypassed is cancelled. We don't need this. Bye-bye. But a little bit hard will be for us, so we can ignore. Emitter follower also cancelled. This is cancelled. Common base, yes, in our example, common base configuration, we have RERC, and same thing, this is the equivalent model. RE, HIP, HP, HIE, and it's the same thing. HIP, it is here. If you compare with RE model, this RE model. RE, H, this is, sorry. Oh, big mistake. Up, alpha IE, and this is here 1 over HOE. So H forward is alpha in minus, or 1 you can write. HIB, it is RE. Directly. Usually, if we have HOE, we can use. If not, we can ignore. So ZI, it is RE with HIP. ZO, we have RC. And AVVO over VI, same thing, minus. If you remember, AV was before, it is was minus RC over alpha. Also RC over RE. Sorry. RE, as explained, it's HIE over HFE IB. So take this up. AV is minus HFB over HIP multiply with RC. AI HPFB, it's C minus 1. I guess now it's easy for you. Hard or easy? Okay, this is example about how we can do implementation. Yeah, so just how we can implement this one here. Complete hybrid equivalent model. It's cancelled this one. But here they explain to us how we can use full model. Example with HRE, HFE, HR, and HO. So if you want to calculate for full model, you can use this one. But for me, it's cancelled because the effect is very small, especially for these parameters. This one is very small effect, and it's all this very small. So if we're going to use it, not affect in the model totally. So HR and HO is very small, so we can ignore it. Clear? Last thing for this chapter is something called hybrid bimodal. So until now, for models, we have RE model, hybrid model, and this is hybrid bimodal. RE is practical model for small signal, medium frequency. Each model is a model for, you can use also for medium frequency. Hybrid model is a model for high frequency, and you can say this is general model, because in this model we'll take in our study the effect of capacitor. Here we have, see, we have two extra capacitor. In RE and hybrid, here we ignore. See, here we will take effect of C. So in RE and hybrid, we ignore C. We can say it's open circuit. So 1 over small frequency 0, so it's open circuit. Because as you know, XC is 1 over 2 by FC. So if here is very small, you can say XC is infinity, that's mean open circuit. But here, see, we cannot say it's open circuit. In this model, we'll take the effect of C in our consideration and our study. So we cannot say it's open circuit. Clear? So now we can say we have two parts. Hybrid and RE, we can ignore here. Effect of frequency, effect of capacitor, because we are using small frequency until for example, 10 kilohertz, 10 megahertz, also same thing. If we arrive to gigahertz or high frequency, we are using hybrid bimodal. Clear? Is it clear for you? Now, in this hybrid, this is, by the way, just you have to know this in exam, and why we are using this model. When I was like we studied this model. We studied this model, full model. We didn't start from R. We start with this one. Here R by RO, RB, and RE. If you want to compare, this is etc. capacitor 1, 2, 3R, etc. R by equal RE. RO equal RO in RE model. Beta IB equal beta IB. This is R by, sorry, by model. This is E model, RE model. So what is the difference? Let's check again if it's correct or not. Okay. In your book, R by this one is beta RE. Yes, as I said here. C by and C mu are given in usually. GM is 1 over RE. RO is 1 over HOE. And here you calculate HRE, it's R by over RO. I don't need this in exam, but you have to know this frequency and where we can use this frequency. And again, if you start with usually this one, this one, this one, this one are given from catalog. So this is, and this is are like what we said before in RE model. So again, if you start with RE model, hybrid model, and R by model will be easy for you. I don't need this, but just where we can use this one. 5.23, this is cancelled. End of this book and this chapter, all of these are cancelled. So until here. Sound model light source is cancelled. So we have a summary. So again, conclusion today. Today we started 2 models, extra models. We focused about hybrid model, and we started with hybrid model. We explained that in 2 ports we have 4 models: Z model, Y model, hybrid model, and S model. We start with hybrid model, and I explain why it's hybrid model, because first one is V, another one is I, and after that we start from RE to find. And we said why we are going to use hybrid, because in RE we have 1 arrow up, 1 arrow down for current. So here in hybrid we have both are down, but we change the sign. So as you see, we have minus alpha. That means we inverse the value instead of inverse the direction of arrow. After that, we started with explanation how we can convert from RE model to hybrid model in fixed bias configuration and voltage divider configuration and common base configuration. Then we went to the last model. It's called R by model, and I will say this R by. Here we can see the effect of capacitor. We can see in R by and RMU capacitor, and majority both R by and mu are given in the question if we have like this model. I told you in our study, for me, I'm talking about myself, we start with R by mode because it's the general one. In our book here, we start with RE because here it's easy one. Okay, then you have this question about summary for your book. About this one. Just a minute. Then you go to the model, everyone. Okay, that's for today. Any question else? Is it easy? I tried to be easy. Is it easy? And here you can find the formulas in your book. that we're gonna use. We found two mistakes, excuse me, correct in your book. Later return to studio to correct this one. Here we have about how we can use not multisim, AutoCAD or CAD to analysis. And here usually we are using multisim. It's easier than OrCAD, but you can, if you want, OrCAD for analysis.